So if you remember, we had a matrix, right? This was our matrix. And we were trying to find its eigenvalues and eigenvectors, right? We already found its eigenvalues. They were 1 and 2. And for the first eigenvalue, which is 1, I've shown you how to find eigenvector, right? This is just a method. So you basically subtract the eigenvalue from the diagonals, right? And then you figure out a vector such that when you multiply what you get after removing the eigenvalue, you should get 0, right? And we said that there is this ambiguity in the coefficient, like it's not perfectly determined, but we will see that we can actually perfectly determine the coefficient as well with a process called normalization. But we will come to normalization, okay? For now, we have found only one vector corresponding to one eigenvalue. So let me write it down. Eigenvector corresponding to eigenvalue lambda 1 equals to 1 is 1, 0. Okay? Is V1 equals to 1, 0. Let's find the other one. For lambda 2 equals to 2, do you remember? Lambda 2 equals to 2. You again do this. You do 1, 2, 0, 0, but you subtract 2 from here, and you subtract 2 from here, and you are looking for a vector which will make it 0, 0. Okay? So what do we have here? Minus 1, 0, 0, 0. And then let's call it A and B equals 0, 0. So it tells us that A has to be 0, right? A has to be 0. We don't know anything about B. So it's something like this, 0B. Okay? And as I mentioned earlier, you can actually take this coefficient out and basically write that for lambda 2 equals to 2, the V2 is 0, 1. Okay? This was an easy example whereby we went from the matrix to its eigenvalues and eigenvectors. Okay? Any questions at this point about this procedure? It's clear, right? Now let's talk about normalization. Normalization is a procedure with which we normalize things. Okay? So what is normalization? Basically, let me take a vector. Let me take a vector V. Okay? So what I'm going to do is I'm going to first take the Hermitian conjugate of this vector, which is this, by the way. Let's say you have 1 plus I, 2 minus I. Its Hermitian conjugate is basically 1 minus I, 2 plus I. Okay? That's what it is. Now, when you multiply the Hermitian conjugate with the vector itself, what you get is the absolute value squared of this vector. Okay? Let me say that this is the absolute value squared of this vector. Do you have any problems here? It's like taking the absolute value of complex number, but this time you are doing it for a vector. Are you following? Yes? So what we want is to make the absolute value of this vector 1. There was a cough when I said 1, so let me repeat. What you want to say, what you want to achieve is to make the absolute value of the vector 1. Okay? So that it's a unit vector. It's sort of a unit vector. Okay. So how can you do that? You basically think of a vector. Let's say a vector, let's call this vector C equals, it's C times 1, 1. Okay? Do you understand this? C times 1, 1. Maybe I can go with 1, 2. 1, 2 is better. C times 1, 2. Let's find V dagger times V. Let's find the magnitude of V. Okay? The magnitude of V is C star 2 C star, right? Because this is basically C and 2C. Do you agree with this? So what do we get from this multiplication? We get 5 times C star C. C in general is a complex number, yes. So we will get another ambiguity here, but in this course, you will be allowed to do something. Let me come there. So if I want V dagger V to be 1, then what do I need? I need C squared to be 1 over 5. Did you follow this? So I need this. C squared equals 1 over 5. And you have already seen that indeed this situation has infinitely many solutions. Okay? Do you remember this? Z absolute value was 1, then Z was anything. Like Z was e to the I theta. Right? In this course and the midterms and also in the lectures, I will just simply write, I will usually forget about it and will just write C equals to 1 over square root 5. Okay, do we have a deal? Because that's also one of the solutions, and we don't want to confuse ourselves every time with phases. Okay, so I will just write down. So hence, this vector V equals to 1 over square root 5 times 1, 2 is normalized. Did you follow this? Yes? Everyone? So for our case, for the previous matrix, if you remember, there was 1, 0. Sorry. There was 1, 0, and then there was V2, which was 0, 1. How can you normalize this? It is already normalized. Let's see why it is already normal. V dagger V1 is 1, 0 times 0, 1. No, 1, 0 times 1, 0, like this, which is 1. And same here. V2 dagger V2 is 0, 1, 0, 1. Okay? Do you have any questions at this point? Yes.
Since you pick up the real part of C, the solution of C, so can we calculate the size of the and multiply the 1 over to the magnitude to normalize it just simply.
Exactly. That's perfect. Yes, very good point. You can simply do this. You can simply do like any vector equals to 3, 4. Okay? You can simply get the magnitude of this vector, which is, so you simply do this. Let me call V normalized is V divided by its absolute value, right? Which is 3, 4 divided by 3 squared plus 4 squared square root, which gives you 3 over 5, 4 over 5. Okay? Very good. So that's also how you get unit vectors in physics, right? You divide, if you want to get unit vector r, you divide r vector by r vector magnitude. Okay? Good. Very, very good. All right. Let me talk about something. Let me just introduce you to Kronecker delta, because we will start using it. Kronecker delta is this. It's shown like this. Delta nm is 1 if n equals to m, and 0 if n is not equal to m. Okay? Example, delta 1, 1 is 1, delta 1, 2 is 0. That's it. Okay? When they are different, it's 0. So, with this at hand, let's move to projection. Or inner product. So you might remember from physics courses something like A dot B. Okay? Do you remember that? It would correspond to projection. How much of a shadow is there of one vector on top of the other vector, right? That's what it represents. So in our case, when we deal with vectors in a matrix form, this corresponds to A dagger times B. Okay? That's what it corresponds to. So what we were doing is taking projection of a vector on top of itself when we were doing V dagger V. Okay? So just to understand our sentence, if you remember, let's see, we understand what's Hermitian matrix, have real eigenvalues, and their eigenvectors form a complete orthonormal. We are already there. We didn't understand complete yet, but we started understanding orthonormal. So what is normal? You know, right? What is orthogonality? Let's find out that. So if you remember, when two vectors were perpendicular, like this, their dot product would give us 0, right? That's orthogonality. So in our case, orthogonality will correspond to orthogonality corresponds to two vectors having no projection on top of each other. Yes?
Why are we using A dagger instead of normal matrix? Because in the vector form, we use normal vectors, not dagger. So I didn't quite understand.
Okay. Is there anyone in the audience who wants to answer that? No? Well, here's the deal. When we are dealing, very good question, thank you. When we are dealing with vectors, we usually think of them having real coefficients. Don't you agree? Right? So this dagger comes in just because we start using complex values, and we just realize that we have to do that, because if we don't, this is also a vector, right? 1 by 1 vector. And you want to find its magnitude, let's say. If you do 1 minus I times 1 minus I, then you actually don't get a real value. So you have to introduce this dagger instead of transpose when you start doing this. The reason is that the coefficients are complex valued. Thank you very much. Okay. So now we understand orthogonality, normality, and we are claiming that the vectors are orthonormal. So let's see if they are orthonormal or not. Vectors being orthonormal means that Vn dagger times Vm is equal to delta Nm. This is orthonormality. What does it mean? It means that if I get V1 dagger V1, it's 1. Let's see. Our vector was 1, 0. Do you remember the matrix produced 1, 0 and 0, 1? So 1, 0, 1, 0 is 1, right? But if I do V1 dagger V2, then I have to get 0. Let's see if that is the case. So I multiply 1, 0 by 0, 1. What do I get? I get 0. Okay? Are you happy? You are confused a little bit?
Yeah, but that's because I have a biology major.
Yes.
The calculus 5 years ago.
Yes. But it's not hopeless, right?
Hope not.
It's almost hopeless. No, don't worry. You will do just fine. So I explained orthogonality and normalization. Together, it's orthonormality. Now that you have orthonormal vectors, let me show you what you can do with them. Yes, sure.
Why do you use delta and m? Is it in a general proof of the orthonormality of the
And I'm using it just as a shortcut. Like when n and m, instead of writing it as a long sentence, I just put delta nm. And you understand that when n and m is equal, it's 1. When n and m are different, it's 0. It's just a shortcut. So complete basis is what you have when you can write any vector as combination of two vectors. Not two vectors, n vectors actually. But for now, let's go with 2 dimensions. So what this one is claiming is any vector can be written as combination, linear combination of V1 and V2. Okay? So where are you going to find these coefficients? In this particular example, it's easy to see. AB equals to C1 times 1, 0 plus C2 times 0, 1. So what is C1? A. Does everyone agree? A. And what is C2? B. Very good. So let me show you how you can find C1 and C2 in any case. Okay, you might think that this will go away, we will see this, and it will go away, and we will not see it again. We will keep seeing it again and again and again. So make sure that you understand this part. If you have any questions, ask now, please. Yes?
Hocam V1 and V2 are just arbitrary.
Yes, but I used our particular example now. Okay, you are right. It can be any vector. So let's talk about that. So let's talk about f vector, a vector, being represented by C1 V1 plus C2 V2. And V1 and V2 are any orthonormal vectors. They have to be orthonormal for this to work. So what do? To find C1, I multiply both sides with V1 dagger from the left. So I multiply. So C1 is a coefficient, so I take C1 to the left. Did you follow what I did here? Everyone? Yes? So what is V1? 0. This is 0. Very good. What is this? 1. So do you see? We got C1 by daggering it with V1. Do you see it? So you can actually find any of these coefficients by doing this. So if you want to find Cn, you can just Vn dagger F. Why there's F1? Sorry. So you can find any coefficient by doing this. Let me actually write it down one more time. F equals to C1 V1, C2 V2, C3 V3, etc. Okay? Something like this, where V1, V2, V3 are orthonormal. They are these orthonormal vectors that came out of this Hermitian matrix. Okay? Then you can find Cn by doing Vn dagger F. Okay? Good. So that's what we call forming a complete basis. Okay? Do we understand the sentence now? So we also understood this part and basis part. Just for completeness, let me write it down again. So we started with a matrix, Hermitian matrix. And what came out are lambda 1, lambda 2, lambda 3, etc. from this, and corresponding V1, V2, V3, okay, which we normalized. Once we normalized them, we have this property, and because of that property, we can write F as the summation of Cn Vn, n going from 1 to whatever it is, and Cn where Cn is Vn dagger F. Okay? All right. The importance of this will be apparent in a few lessons, I guess. So just when you thought that it can't get any complicated than this, okay, I would like you to now think about infinite dimensions. Okay, we have a vector of 1, 0, 1, 2, 3. Now take that to infinity. Take the vectors to infinity and start thinking about functions as infinite vectors. What do I mean by that? I mean this. You have a function, right? Let's say goes like this, and for each value of x, for x5, there is fx5. Let me just name it f5. For x7, you have f7, etc. Right? Now, I want you to think about this fx's organized like this. And it goes on forever because indeed you actually have infinite number of x's. Don't you have that? You do have that, right? There are, for any x, there is a function, so think about it as a vector. If you have trouble thinking about it, then I don't know if this will help or not, but you can chop it down to certain points, certain finite number of points. Maybe you are going to plot it in a computer, so you maybe can't tell the computer just plot sine x. You have to tell it like what is sine x at each individual point. So you decide on a resolution. Let's say from 0 to 1, I'm going to represent it with 100 points, so that you can make this infinite thing a finite thing in a computer or in your mind, right? Just you are making a grid of x, and in each grid you place the value of that function. Okay, now let's think about functions forming orthonormal bases. Functions forming orthonormal bases. What could it mean? Since we started thinking about functions as infinite dimensional vectors, it's just the same thing. Just like vectors can make an orthonormal basis, functions also can create orthonormal bases. And we are going to be interested in particular one of them, which is this one. Let me just plot it. So I have y-axis, x-axis, and let me plot a sine for you. Okay, this is my sine. Let me see if I can use technology. Can I actually rotate it? Sorry. Or take it down like this, maybe. I want this to look pretty, so just give me time. Style. Yes. So this is A. Let's say this is from 0 to A, and this one is sine pi x over A. So when x is a, it's sine pi, so it just has one hump. And this one is sine 2 pi x over a. Okay? And I'm going to claim that you can make them orthonormal. You can make these functions orthonormal. We need to figure out what we mean by orthonormality for these functions. So, of course, there is some coefficient in front of it. Let me say some c coefficient, c1, c2. Okay, this is f2, this is f1. But for now, let's imagine these functions together. So there is f1, which corresponds of sine pi x over a, evaluated here, and f2, which has sine 2 pi x over a, evaluated here, right? Those values, just listed. So what do you need to make it, first of all, normal? How do you normalize it? You have to do f dagger, f1 dagger, f1, and it should be 1, right? What does f1 dagger mean in our case when they are vectors? It means that you take this, you conjugate them, you conjugate those values, and you multiply with the other ones. So this is f1 star values and f1. So when you multiply this, what do you get? So you took the function, you put it like this, you multiply it with this one, yes? You get the transpose and complex conjugate of it, multiply it with this one. So they are multiplied individually. This one with this one with that one, this one with that one.
So there's an integral?
There is an integral, yes, very good. So this can be represented as an integral. Okay. Before going to integral, let's start with, okay. Isn't this going to be summation of f at x1, xn times f at xn, and going from 1 to infinity? Isn't it the case? Yes? Does everyone agree? What is this? It's an integral, right? So you know that summation can always turn into an integral, right? Okay? So we have reached to this conclusion that we can represent this orthogonality or orthonormality, the normalization and being perpendicular, in terms of an integral. So let's integrate this. Let's integrate f1 star f1 dx from 0 to a. Let's see where it goes. Okay? Just bear with me, we will go somewhere. So c1 star sine pi x over a times c1 times sine pi x over a dx integral from 0 to a. Did you follow this? Yes.
I want to ask something. Why are we using stars in integrals? Aren't stable values with fn, fxn, stars with fxn?
If the function is real function, real valued function, yes, that is the case. But the function in general can be a complex function. Okay? That's why when you transpose it, you also conjugate it. Okay? Why we are interested in complex function? Because we are going to do quantum mechanics. Okay? So let's do this integral C1 star C1, which is C1 magnitude squared, right? And we need to evaluate this integral sine squared pi x over a dx. Okay? Anybody knows what this integral is? Oh, let's go that way. Yes. 1 minus. Is there a 2 there or 1/2? The whole thing is 1/2, right? 1/2 cosine 2 pi x over a, right? Integral from 0 to a. Very good. So you get 1/2 times a, right? And minus integral from 0 to a cosine 2 pi x over a divided by 2. And that integral is 0. So what do you get? You get 1/2 a. Okay? So what we realized is that f1 star f1 integral dx from 0 to a turned out to be c1 squared a over 2. Okay? Now, if we want this to be 1, because we want it to be normalized, are you following the storyline? Hopefully. If we want this to be 1, then c1 absolute value squared need to be 2 over a. Then in this course, we are just going to get c1 equals square root 2 over a. Okay? So let me just tell you that for f2 star f2, you also do get c2 squared a over 2. It doesn't matter whether it's sine squared pi x over a or sine squared 2 pi x over a. The integral is a over 2 in both cases. And it can be any n, sine squared n pi x over a, where n is integer. You will get 2 over a. Okay, I don't want to bore you with mathematics. Not that much. This much is okay. So c2 will also be square root 2 over a. That's my point. So we have two functions now. We have f1 equals 2 over square root 2 over a sine pi x over a and square root 2 over a sine 2 pi x over a. And they are normalized. They are normal. What do we need to do to figure out whether they are orthogonal or not? Do you remember orthogonality? No? Yes? What was it? You look at this, right? So you take the integral f1 times f2, f1 star times f2 dx. And that's basically going to give you 0. How do I know this? Let me write you a general formula for this. Okay? Let me write you a general formula. Let's say fn is square root 2 over a sine n pi x over a. Okay? You can try it at home. Then the integral from 0 to a of fn star fm dx is delta nm. Okay? That's how we know it. And this is just, in previous courses, I used to derive it like this. And now I'm not deriving it. I've learned my lesson. So this is what we have. So what we have achieved the following. We have figured out that these functions, fn equals to this, are forming a complete orthonormal basis. They are forming a complete orthonormal basis. What does it mean? It means that any function, any analytical function, probably, I have to say that, probably. Do I have to say that? Yes? Otherwise it doesn't work, right? If there are jumps in the function, can science actually capture that? Okay. Okay, very good. So any function gx can be represented as the sum of gx. Let's say I want to represent it as c1 f1 of x, c2 f2 of x, dot dot dot. Okay, it continues like that. Can you guess how I can find cn? Let's do it actually. Let's multiply both sides with fn from the left. So let's say I'm multiplying fn star gx, okay, equals to fn star cn fn, right? And I'm going to integrate. Okay. What do I get over here? For example, there is, I'm sorry, I have to write different names here. So whenever fn is equal to fm, then I'm going to pick up that value, right? I'm going to pick up cn times 1. But otherwise, I'm going to pick up 0. Do you see it? Yes? So let me just write it down like this. Cn is going to be integral fn star x gx dx 0 to a. That's how you find the coefficients. Again, let me spoil what's coming and tell you that these coefficients will have physical meaning, okay? These coefficients will tell you their squares will correspond to probability of getting a certain output from measurement. Let's say you are going to measure the energy of the system, okay? We are dealing with energy. Then we have the corresponding matrix to it, okay? The corresponding matrix has its eigenfunctions and eigenvectors. We represent our state in terms of those eigenfunctions and eigenvectors. And while we are doing so, we are getting these coefficients. And the squares of those coefficients will tell us what are the probabilities of getting a certain energy, okay? It's not going to waste. I know it's hard. It's not easy. I know. But it's also very, very useful, very, very central to this course. Sure.
Is the reason you consider only the sine function is that we can write all the function beside the sine function, or is
Well, why I showed you sine function is because although I keep saying that quantum mechanics, at the end of the year, you will realize that you have learned only 3 systems in quantum mechanics: particle in a box, harmonic oscillator, and maybe a little bit of hydrogen atom. Okay? But particle in a box solutions are signs. So that's why I use signs, because although right now you are having this cultural shock, having it together with quantum mechanics would be even harder. So I'm exposing you to this shock now, so that when quantum mechanics comes, you will say, these are signs which are orthogonal, no problem. Okay? So they are going to be solutions of particle in a box system in quantum mechanics.
But
They are also major part of Fourier series. I'm aware of this one as well. That's your question, right?
yeah, I know
Yes.
the reason you consider the sign function.
Yes. All right. I have one more point, but to make that point, I need more than 4 minutes. But let me just prepare you for that point. The next time we are going to talk about differential operators. Operators as infinite dimensional matrices. So we have thought about functions as infinite dimensional vectors. Then what is the corresponding thing in matrices, right? Matrices going to infinite dimensions. And this time it's going to be differential operators. Like, this is just one of the examples, but it's the most important one. So let me in particular talk about d squared f over dx squared. So think of it this way. There is d squared over dx squared operating on function f. And function f is already, we have thought about it, it's infinite dimensional vector. Okay? What is then this one? It turns out that this is a matrix. Okay? Why it is a matrix? Let me go as far as I can, then we stop. This is a matrix because how do you define this? D squared f over dx squared. It's d over dx of d over dx, right? It's the derivative of the derivative. So how do you define the derivative? Let's say you have a function, okay, and let me pick 3 points. 1, 2, 3. How do you define the derivative over here? It's basically f3 minus f2 over delta x. Do you agree? That's the derivative over there. How do you define the derivative over here? It's f2 minus f1 over delta x. Yes? That's basically the derivative over here and the derivative over here. So far, so good? Now let's find the derivative of the derivative. For that one, you do okay, let me use colors. f3 minus f2 over delta x minus, exactly, this one minus that one divided by delta x. Okay, so what we have achieved, del squared f2 over dx squared. So the evaluation of second derivative at the point 2, you see the point 2 is in between these 2 points, right? So it's actually the second derivative at the point 2 over here. And that derivative turns out to be f3 plus f1 minus 2 f2 over delta x squared. Okay, let's stop here and then we will go to the matrix.